So today we will be talking about one of the topics in quantum mechanics. I think math as well, about eigenvalues and eigenfunction. Eigenvalues and eigenfunction, vectors, sorry, not functions, vectors. So to get started with, we will talk about, or wait, let me give, since we're talking about vector and values, we need a graph. Okay, so in graph, let's add the spaces, more spaces. Yeah, over here, perfect. Oh, just, yeah, okay, yeah, good. So let's suppose if we have this over here, graph, and y and x, and we have two bases, one line which is in x-axis and one line which is in y-axis. Their coordinates are in terms of vectors, because this is all about vector. So we'll this coordinate is 3 0, and this is what is that? 2, sorry, 0 2. Okay, so its vector will be this, right? I think it will be how much? For the sake of the video, we'll just go with examples. Okay, whatever this vector is, the property of this vector, if we stretch this graph, okay, if we stretch this graph, and the line, the vector which is going through, which was made, if there's no change in this line, the point, even though we move it to a certain vector like this, transform or stretch it, and if this line displaces itself to another position, that means it's like it has a moving span. We call it a moving span. But there are some spans, there's some vectors which don't move even if you stretch or transform the let's go with stretch, even if you stretch them. Okay, and that is over here in this part, the vector or the matrices -1 and 1. This matrix vector, even though you change or you stretch the graph, this line of span won't change its position. It will stay the same way no matter how you stretch it. And even if you will stretch it, the amount of increase you will get is, scaling factor is 2. Every time you will get a increase of 2. And along the x-axis, this is a diagonal axis, it's called a diagonal axis. Okay, and the other one which is along the x-axis, the main thing about that one is that it will every time stretch with the factor of 3. So if you zoom in or zoom out, the scaling factor will be 3. So you might have guessed, yes, this is what the eigenvalues and eigenfunctions are. The line or the change which doesn't happen with the transformation or stretching of the graph, this line over here, the unchanged line, is nothing but the eigenvector, and the value of the scaling factor which we have when we stretch this line is the the stretch is eigen value. Okay, eigenvalue. Then so these are the eigen, the line or the line and the line and the stretch. So the eigenvalues and eigenfunctions. Okay. So in terms of equation, how I would write it is as special symbol A, and this is a transformation vector matrix, transformation matrix, some special symbol lambda, and some special symbol lambda and with v again. So these two are here our eigenvectors. The v, the special v's are eigenvectors, and this lambda over here tells us that amount with which we have to move the graph so that our two equations equal each other. So if it's like this, so the matrix for the lambda, the matrix of lambda, because in this is lambda and it's written as so then what the main thing is, the main thing